I'm going to make it a little tougher this time than I did last time. The phenomenon I'm talking about now is the theory of the electricity, light, and so forth, and we're concentrating on first tonight light, and next Tuesday, it'll be about electricity, and finally we're putting the two of them together. And the next lecture after that, we'll talk about what's wrong with the theory and what's in the world besides electricity and light, what else there is in physics, and what new questions are up. But in the meantime, I'd like to talk about light. Newton started by many experiments and observations which began this subject. He found there are phenomena that are so very, very common, but are absolutely sensational, ununderstandable, and almost impossible, supposing that light is made out of corpuscles or particles. Newton assumed that light was made out of corpuscles or particles because he made a mistake in reasoning. He said that he thought that the shadow edges were very sharp, and that meant that it must be particles, because if it were waves that went past the shadow, they would spread into the shadow. This is a misunderstanding of exactly how waves do in fact behave. They do spread a little tiny bit into the shadow, and the shadow spreads into the light of it, but not very seriously. And in fact, the wave theory of light is much easier. It finds the phenomena that Newton discovered much easier to explain. But I'm going to start by taking the view that light is corpuscular, that Newton had, and remind you of what these phenomena are, and then go back over Newton's attempt to explain them and see how pitiful it is. So we start with the reflection of light from a surface of glass. Last time I used water, and I said it was 2% reflecting, and somewhere along the line I changed it to 1/4, and that was a mistake. It's glass that's a quarter, and water that's a 50th. 2% is not a quarter. I mean 1/25th. It's 2% is 1/50th, and for glass it's 4% or 1/25th. So we'll talk about glass. The first feature that's interesting is that from glass the light is reflected only partially, and if it's particles it means some of them have come back, 1 out of 25, and some go forward. 24 out of 25. There's nothing too hard about that. If you would suppose something is different from one particle to the other, even in their arrangement or something like that, but further experiments have all shown that all light photons are exactly the same and in the same condition, and there's nothing we can do to preset the photon to make it more likely to come back from the surface, a single surface of water, than to go forward. There's no way. And we have, well, I'll keep on going from a simpler point of view, and we'll discuss other models in a minute. But the really interesting feature is that the reflection of light from a glass surface is affected if there's another glass surface below it. For example, if you have a soap bubble, which is the surface between air and water and air, then the two layers make colors in the bubble, which aren't in the water, but is produced by the effect of the reflection from the two surfaces. And if I choose light of a particular color, say if I looked at the bubble with purely yellow light, then I would see rings or areas that are black and areas that are bright yellow, relatively. In other words, areas that reflect well and areas that do not reflect at all. In other words, the reflection from a surface, which you would expect from a single surface, can be reduced to zero by putting another surface here, which common sense would imply would increase the reflection. But it could, in fact, make the total reflection zero. And the actual reflection probability, chance that the photon or corpuscle gets reflected, varies with the thickness of the layer this way. If the thickness of the layer is 0, it doesn't get reflected at all. That's nice. No glass, no reflection. If the glass gets thicker, the reflection increases to a certain peak. But if the glass is still thicker, the reflection falls again to 0, as I said, and rises and falls and so forth in a repetitious fashion. Newton, believe it or not, and only working with very thin layers first, discovered this with 3 or 4 at 10 repetitions, and then was able by a clever experiment to demonstrate that it happened after 34,458 repetitions. In other words, with a quarter of an inch of thickness, this bumpy thing was still going. Nowadays, we can do this experiment in which these two reflections are separated by so far a meter or more, and if the conditions are just right, you get monochromatic light of exactly one color from a laser, you can still see as you move this thing, reflection strong, weak, strong, weak, strong, weak from the two surfaces. So it goes on forever. Now, how can we explain such a thing from the point of view of corpuscles? I do this to show you what a fix Newton was in, to explain it, because he thought it must be corpuscles. First, the reflection must depend on both surfaces, because it depends on the distance between them, for example. Also, he noticed that the wet one or the other surface to change the reflection. So they're both involved. Yet it can't be that the particle is reflected from the first surface, because if it were reflected from the first surface, it would never know where the second surface is, and the net reflection depends upon the position of the first surface. For example, if it was reflected from the first surface, how could it be not reflected at all if there's a second surface at just the right distance? And therefore, it must be entirely reflected from the second surface. But the reflection from the second surface is affected by the position of the first one, and therefore it must be as follows. The first one generates an influence which generates some kind of a wave in a medium or something of a kind that follows the particle along and changes its disposition to be reflected or not reflected. That is, it gets the particle of light as it comes through, can be in different conditions, either a condition of easy reflection or easy transmission, the opposite, no reflection. And whether it's easy reflection or easy transmission is determined by some kind of an influence which propagates along from the front surface and overtakes the light particle and adjusts it, so to speak, to make sure which way it's going. Now, this had a lot of difficulties with it. It was called a theory of fits of reflection and transmission. It's not good for the following reason. You can't get along very well with the idea that it's not reflected at all from the front surface. Because suppose you had very deep water, just a little dirt in it, then you still see the reflection just as well. And if it's not reflected from the first surface, it's impossible to explain, because that stuff which is coming, looking for the bottom surface never gets there, and yet some light is reflected. Second, if it's all the decision about reflection is made at the second surface, then it should not be expected that it would be possible to alter that decision by putting in a third surface. Now, Newton did not have available the experiment in which he used more than two surfaces. But had he done that, he would have found that the amount of reflection is altered again by the presence of third and fourth surfaces. And even though with two surfaces one might get a very strong reflection, by putting more surfaces underneath, you can reduce that again to 0. So that the decision is not being made on the second surface. The decision is made on the last surface. Then how does it know as it's going along whether there's going to be a last surface or not? Now, Newton I would say is a genius about something. Actually, he's a teacher of something. He's the man who taught us how to do or how to think about science in a modern way so that we can make some progress. He's the one who distinguished very carefully between the facts that he would develop and experimentally determine this really happened. That is to say, what really happens is that the amount of light or brightness does go up and down depending on the thickness. And that is to be distinguished from a theory to explain why it's so. He hasn't got a satisfactory theory. He did his best. I'm sure, I can tell from reading it, that in the back of his mind he knows there's something the matter with him. He knows the explanation is going to get him into trouble for somewhere. He can feel it. because he puts that part in the form of queries or questions of how does it work. Can it not be that there's a part, influence which propagates along and overtakes the light and so forth? He doesn't say there is. This is going to get into difficulty. Now you're all happily laughing at poor Newton, but you have to laugh at yourself, because you live in the world and this happens, and you have these very good ideas about how things happen, and you can't figure out how such a thing can happen from common sense ideas. Save one possibility. It's not particles. All right? And so it turned out that people proposed that instead light is waves which come down, and like waves in the sea, and parts of them bounce back here and they bounce back here, and the crests come together under some circumstances of timing, and the crest or troughs come together under other circumstances, and you get strong or weak waves going out, and that's what you see in brightness is the strength of waves. So that for many years, it was all these wonderful phenomena were happily explained by the wave theory of light. And the difficulty there, the idea there was that if you had a very dim light, the wave, that would represent waves hardly moving at all. Just a little motion, carrying very little energy. So when they went to investigate dim light with the most sensitive instruments to see what it looked like, you found that the dim light wouldn't make an instrument like a photomultiplier or any other device that was very sensitive go off, said there's a certain amount of energy here. Well, there's nothing. There's a bump of energy. The energy came in lumps. It wasn't a tiny little bit dribbling in all the time. And so the experiments with photomultipliers, which I unfortunately don't have a direct experience with, but the characteristics of them are that light is made like a corpuscle, so that although Newton's logic as to why they have to be corpuscles was wrong, it turned out he was right about there having to be corpuscles. And his paroxysms of reasoning that were produced by this thing, the torture of the mind that's produced by this phenomena, plus the fact that light is corpuscle, was returned to the physicist as a real problem. And it has never been solved in a completely, well, it's solved in a way, in a description method by which we can predict what happens here. What happens here is that this is not the intensity of a wave, that is the amount of wiggling of the wave of some kind, but it's instead the chance that a particle comes as being counted by a photomultiplier. When I have the thickness so big, so and so many particles come, if I sent a light so weak there was only one particle, I send only one corpuscle, one particle of energy, one photon to this system, and sometimes it bounces back, and sometimes it goes forward, and this gives you the odds that it bounces back and goes forward. For a single layer, the odds would be 4%. This maximum height here is 8%, and 4% around here, and it can go down to 0. Now, we have not been able to find any system of logic that's consonant with ordinary ideas of causality and ordinary ideas about what things go. How can it not know when it's at the front surface, it's in the back surface, all that stuff that'll explain this or describe this. And so in order to keep going, in order to describe nature, we've had to generate a set of ideas which are empty of, a set of rules, rather, which describe how to figure out these probabilities, which are empty of models. That is to say, empty of a model of the type you're expecting. A particle is like a billiard ball that bounces against a wall and so forth. It doesn't work. Or that it's like waves. And what I would describe last time to you was this picture. I would say that it was in about the beginnings of the 1900s that it was discovered that light, as a matter of fact, behaved like particles, which was a terrible shock after the great success of the wave theory. And then the problem of trying to see how particles could make these wave-like phenomena that are so easily explained by waves became known as the wave-particle duality. Things would be said like light behaves as particles on Thursdays and on waves on Tuesdays, and that, of course, is not a satisfactory theory. The quantum mechanical, it turned out as a quantum mechanics study further that light is not unique in this connection, that things that were supposed to be honest, proper particles like electrons behave sometimes, produced effects like this, exactly the analogous. So things that start out as waves behave like particles, and things that start out as particles behave like waves, until both, it was clear, behave the same way. They behaved in their own inimitable quantum mechanical way. It worked out in 1926. At first, the equations were discovered, and then it was, in fact, a man you don't hear of very much when they talk about quantum mechanics, a man named Born, who proposed. Somebody's blowing their nose in. Max Born, who proposed the interpretation of the equation in terms of this idea that we're calculating probabilities of events, that it's a statistical matter, and that it's not possible to predict exactly what will happen in a given experiment. Now I want to repeat the rule that we have here, which looks completely artificial, and I prepared you last time, as you all knew. We had a similar difficulty last time. It's heavy. I'll take it out, okay? All right? Is that all right? Okay. Now, I predict that the probability that I'll have a microphone of that kind next time is very low. All right. Now, how do we describe this in modern physics? First, that we cannot predict what will happen. We can't tell you for a given particle whether it's going to be reflected or not. Horrors of horrors, but it's true. We give up. And second, in order to find the only thing we do calculate is the probability, let's say in this example, that it'll be reflected. More accurately, I should say better, this way, that if you have a source of light here and a photomultiplier here to look, the probability the photomultiplier goes off. That's what I'm calculating. I said the probability that a photon went down and bounced back. That's bad. Otherwise, they get back in the old problem again. Which surface did it bounce from? No. Just the probability that the photomultiplier goes off. All right? Now, how do you find the probability that the photomultiplier goes off? As follows. General. Not only about light, the whole of the world is built this way, according to these modern physicists. It's just an example. Photomultiplying goes off, electron counter goes off, things like that. Probability, you calculate probability of events this way. The probability of an event that comes out in the end is proportional to the size of a circle made by an arrow on a plane, a calculating plane over here. It's got nothing to do with the geometry of that. This arrow on the plane is called the amplitude, sometimes called the probability amplitude for the event. So everything that you want to calculate, the chance that the counter goes off, has a probability. No, it has a probability amplitude. There's an amplitude that it goes off. The square of that is the area, or proportional to the area. Somebody bothered me about a factor pi last time. Correctly, is the measure of the chance that the counter goes off. All right? Now, the theory, that's the framework of nature, and the rest of the theory of nature is to compute these probabilities, amplitudes. That is to tell the rule for finding the length of the arrow and where it's located. And that's what we talked about last time again, and I'm reminding you, in this particular case, it works as follows. For light that's monochromatic of a single color, let's say red, it's the following is the rule. That you draw an arrow for the reflection. Let's say, for instance, that this is, say, a single surface. Reflects, let me suppose, 4%. That is, in fact, 1/25th of the light. So if the unit of light, if the light, one unit of probability is represented by that, and its size circle, when light is reflected, the length of the amplitude arrow is 1/5, because its square is 1/25th. So here's the amplitude arrow for reflection from the front surface. Should be 1/5 the other one. Incidentally, the same manner, the reflection from the back surface produces an amplitude arrow for, this is the amplitude rule 1/5. That's the rule for reflection. And this, from the top surface, this is the corresponding rule from the bottom surface, is to make the 1/5 in the opposite direction. And finally, one more rule, that you have to figure the time to go from the source all the way back to the photomultiplier, if it was going at the speed of light, and the proportional to that time, you move this around like a clock. So the effect of the reflection from the first surface is in fact an amplitude which is 1/5 long, but is tilted at an angle, which is what would result from a very rapidly moving, rotating clock hand going along, as if you wish, for the length of time that you would calculate ordinarily for the light to come to the first surface and bounce back. It goes around like a son of a gun. 1 followed by 15 zeros a second. It's going around. And then when it finally reaches the photomultiplier, it's in some position. Likewise, the second one, this is the first one. Let's say this is the first surface, the second surface, but more correct when you put the timing in. That's the contribution of the first surface. Now, for the other way that the thing can happen, we have the second arrow turned also around a great deal, but not by the same angle. Let's just for a moment suppose that the two surfaces were exactly on top of each other, then the times would be exactly the same, and the angles would be the same, and in that case, the other one would come out this way. But if it's further down, it in general will come out at some other angle, because the time is not the same, so let's draw it at another angle. Now, the rule is this, that if the general rule starts something like this, probability is equal to the square of an amplitude. Amplitude for an event that can happen in more than one way is the sum of the amplitudes for each way. Now, what do I mean by sum? How do you add two funny arrows? Rule for adding arrows, you put one on the tail of the other. So this was number 1 and this is number 2. You draw them like that and see what you get left. So in this particular case, we have only 2 ways. We have only 2 arrows, and I've added them together by making one chase the tail of the other. This is the arrow representing the contribution from the first surface, and that's from the second surface, and you're all bored because I told you all that last time. But hoping that there's a few more, some people, I cannot believe that everybody who was here before came again, and there's the same number of people as there was before, so I deduce that there are some people who weren't here before. Now, this then produces these effects in the following manner. That if the thickness is 0, the first arrow points this way for the case of 0 thickness, say, and for 0 thickness, the second arrow points that way, and if you put this tail on the head of the other one, you go up and back, and the net result is nothing, whose circle is 0, and there's no probability. On the other hand, if you have the thickness, a little bitsy thickness, you got just a little bit more turn, and you get something. That's somewhere up, climbing up here. The best you can do is if you get the thickness just right, so that this one is turned around so it's exactly lined up this way. So with a certain thickness that's just right, the first one is turned a certain angle, and the second one, which would be out here, is turned more by another half turn, and therefore the second one is this way also. And when you put the tails together, you get it twice as long, right? And then you would have had it by one alone. And therefore, what is the probability? 4 times what it would have been for one alone. Because the probability is the size of the area of the circle, and for one alone, if there were only one surface, the circle is only so big, and there's twice the radius is 4 times the area of the circle. So therefore, the height of this is 4 times, the probability here should be 4 times as much as it is from one surface. And since from one surface it's 4%, and 4 times 4 is 16, this has to have been 16. And it is. Now, in this manner, of course, if we take greater thickness, the thing turns around further and further, and it goes down again, gets back into the same condition in a repetitious fashion when the timings are so. And so we understand why this keeps on going up and down, up and down, up and down. No, I'm sorry, we don't understand a damn thing, but we have described how it behaves. you'll notice that the average here, if you had some circumstance in which you average this and didn't look too closely at the thicknesses, you had an irregular plate or something like that, or for any other reason you want to average it, the average is about halfway up. In fact, it turns out, because of the symmetry of the curve, to be exactly halfway up, and the average is 8%, which is the amount of light that you would get expected to have gotten if 4% came from the front and 4% came from the back, and our life was easy. If it weren't for these bumps, there'd be nothing to that. We could understand 8% childishly, 4% from coming from the first surface and 4% coming from the second surface, but it doesn't do it that way. It sometimes gives us, instead of 8%, nothing, and other times it gives us 16%, which is more than we want, and it ends up, on the average, giving us 8%. And it gives a clue of how the old theories, the simple-minded views of what was happening, what happens in the world, why you can bounce balls and count things and do things as you expect them to do, works. It happens that these irregularities involve this distance of thickness is something like thickness of glass of the general nature of 10/1,000,000th of an inch. And therefore, for ordinary pieces of stuff with reasonable dimensions in which you're not so accurate as 10/1,000,000th of an inch, you're doing a lot of averaging, and then common sense dumb stuff like, look, it reflects 4% on the front surface and 4% on the back surface. It's got to reflect 8. Come out right. But that's because you're averaging all this fancy business with these arrows. Now, what I would like to do in this lecture is to show you, to start you off in a certain direction and to show how it is that although this model of the world is so thoroughly and utterly different than anything you've ever seen before, or expect and hope never to see again, it will explain the simple properties of light that you know. And properties such as angle of incidence equals angle of reflection, that's in there. That light goes in straight lines, that's in there. That light, when it goes from air to water, it deflects. The light goes in a certain line, you know, and when light goes from air to water, it changes direction. Yes, all that's in there. That if you have a lens, you can focus light to a point, and things like that. All of that's contained in this thing, plus many other phenomena. And the great difficulty I had with this lecture was this. It's so easy to derive all these phenomena that you take so long to learn about in school that I did one after the other until I found I was doing too many. And then I realized I'm doing it to people who know that. For example, what is the exact behavior? How much does light go into a shadow? I wanted to explain. It's easy, but I'm not. But since not many people know how much it really, how it looks, they haven't seen diffraction anywhere, I won't bother with that phenomenon. So what I had to do is to control myself and not produce a large number of examples, but only a few, to show you how it starts. But I can guarantee you, of course, because otherwise it would be illegitimate what I've been saying, that all this agrees exactly with every phenomenon that everybody has ever observed with light, every detailed phenomenon. So I'm just going to start with the simplest possible ones that are common. All right? We start with a mirror. We start with the problem of determining how light is reflected from a mirror. And we have here a source of light, and here the photoelectric cell, which is, a photo multiplier that's going to measure very low intensity light. We have one photon at a time go here through here, and we would like to know what the chance is that this thing gives a count. It's also possible if the light goes straight across. To avoid that, we put a black box in here. So we have to think, and we would expect that what we'd have is that the light would reflect from the mirror like so, and that's what we usually say, and that all you need is this piece in the mirror here. This got nothing to do with the price of cheese under these circumstances, right? And that, in fact, the place where it reflects is where the angles are equal. That might be obvious to you because it's so darn symmetrical, but if I put this thing further down, you can still prove the angles are equal, and I'll show why it is. By this rule? Yes, sir. As follows. Rule. Probability that a thing occurs is a square of an amplitude. Amplitude is the sum of the amplitude for every way that the thing can happen. In that experiment, there were 2 ways it could happen. In this experiment, there's virtually an infinite number of ways it can happen. To make it easier to understand, suppose that this mirror surface was temporarily divided into little squares. It's best if the mind forgets for a while that there's another dimension to this mirror this way. This is a cross-section of the mirror. And just for the hell of it, I can forget that, but we can do it the other way too. Now what happens is that there's several ways in which the photon could have gone to the photomultiplier. It could have come down to this part of the mirror and bounced off and went to here. You're crazy. The angle ain't equal. I'm not crazy. That's what happened. Another possibility is it could come here and go. Or it could come here and go. Or it could come where you'd like it to come and go. And it can go over here and go, and so on, and so on. And these are all possibilities. And the idea is that there's a certain amplitude that it does it this way, an amplitude that it does it that way, and so on. And now we have to figure out the total probability that it does it at all. Naturally, instinctively, you're going to, I'm going to tell you the rule that the amplitude is biggest for the one where the angles are equal. No. The amplitudes there's slight variations, which we're not going to worry about them. It's almost the same for this one as for that one. Let us take it easy. We make approximations here to make it easy to do, and I'm not going to absolutely exactly mathematically. I just want to explain the idea. I'm going to suppose it's exactly the same amplitude for every one of these things. But the timing is different. That is, let's suppose that the rule of that your chance that you get the amplitude to be reflected in a little square here, there's some little arrow. Very small, I draw it. But because I have to count the total time to go from here to here to here, this arrow, the contribution of this one, gets rotated, zing, depends upon this time. And the one to go from here to here is also rotated, but not by the same amount. Because I think you can almost see that the distance from here to here is certainly not the same as the total distance from there to there. There's a time it would take. It's not obvious? All right, then let's take a place way over here. The time it would take to go over here and then go rushing off to here is certainly longer than it would take to go the easy way. And in fact, if you were in a hurry and you had to run over to this wall and run back, you'd know more or less that the best way to do it is somewhere in the middle there. And it isn't a good idea to run to the wall here and then have to go back. So what we're going to do here is to figure this out by a series of drawings to help us calculate. The second drawing underneath here is a kind of a graph. Let's see if I can do this with colors by some. I don't know how to do it with colors because I didn't figure it out ahead of time. But this is a graph in which I measure this way. Yeah, let's do it this way. The time that it would take to go from here to the mirror and over here, and I'm plotting it this way, directly under the place where I want it to go in the mirror, see? Now, the time it takes to go here, we just found out was pretty large, and going down, more or less, as we got near the center, and of course it's a kind of a symmetric curve, and it goes up here. What do I mean by this? Let's make it very definite. If you're going to reflect from this point here, this particular route, then this is the amount of time. This height is a graph of the amount of time. There's a lot of time. If, on the other hand, colors. If, on the other hand, you were to go somewhere nearer the middle and come down this way and go so, then the time it would take is less. And it's plotted on this scale as this height from here to here. You don't have to worry about the plot if you understand the idea. The time is big, comes down, and goes back up again. That's all, depending on where you are. And now what does that mean for our arrows? It means this. The contribution from this one corresponds to an arrow like this, a little baby arrow. Baby because I make these things very tiny in the end. I told you in the last lecture that we have learned that students take 4 years of undergraduate work plus 4 years of graduate work to learn how to add these arrows cleverly and quickly. And we'll just do some simple examples. So I tell you what, we'll have to just work it out ourselves for 1 or 2 examples. But that's all they learn is how to add the arrows. Now what you do here is you take this arrow and you turn it around a lot, that's I call a lot, from here to here, and you come out with the arrow in some direction because it's spun around at so much time. Now on the next point here, which I didn't draw in a color, but just let's talk about it, is less time. It doesn't turn around as much. It's more like that, okay? The next one is less time. It doesn't turn around as much. I should be coming toward the green one in case. In this term, it's not, well, let's say this one's around here, and this one, you see, what I want to point out, that well, I didn't do it too well, but that the change is less each time as I go along. That this one is, I don't mean that it's an accident that it comes out nearly horizontal. I don't care where it came out, but unfortunately it's nearly horizontal. Let's say that the next one is hardly any change from this and corresponds perhaps to that direction. There's no meaning to the absolute fact that it happened to come out that way. But it's important to point out that as I go on to the other side, the timing is increasing again, and so the contribution, the arrow I would have to draw to correspond to the contribution from this would be again slightly inclined. As I went further over, the inclination would increase again further and further. If I do it very carefully, I should have at corresponding places out this side the same kind of arrows as on this side. In other words, the contribution that's made according to this dopey rule that to get the total amplitude that the thing arrives over there, square is the probability. We have to add an amplitude for each root, and each amplitude is the same except that turns at different degrees depending on the time. And now I have to add all these things together. Of course, it goes on both sides of the mirror way out, and it's hard to get started because they're way over here. But let me just start over here, or further back. What happens is I'm going to put the arrows on each other's tail. This one represents the first one here, and now this one comes. You see, I put the arrows on each other's tail. And then the next one, it isn't working out too clear. It's hard to make the drawing clear, but maybe you'll believe me when I tell you what happens if you do it very carefully. And then it comes an arrow this way, and then the green one, which is hardly any difference in direction. And then the next pink one, that's just tilted up there a little bit again, and then tilted up some more, and then tilted up some more, and then tilted way back. And now let's, for the fun of it, keep on going. Yeah? But what will happen is the things that get turned more and more and turns more and more. So the next one's this way, and 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 the next one's this way. Okay? Boom. And in the same way, the stuff that I hadn't drawn yet over there correspond to an arrow tilted still further cockeyed and still further cockeyed until so on, all knotted up in little things. Now that from one edge of the mirror, which is the 74th arrow over there that I know, to the other edge of the mirror, which is a 7 millionth actually arrow, because it's usually with a reasonably sized mirror, since these angles turns involve millionths of an inch, there are millions of turns. So that this got down to really down in the middle here, and it goes to the middle here. And so that the total amplitude, which is the sum of all these arrows added together, of which last time I added 2, I now add 3, no, I add 5, no, I add millions of them. I get a line for the net result of the whole thing, the total amplitude to arrive, which is this tremendous line from here to here, as the result of all those little arrows. Okay? Now, let's investigate. What determines how long that line is? The size of that square determines the probability. Now we notice a number of things. First, that the edges of the mirror are not important. That were I to have chopped a piece of the mirror off over here, a piece that you had intuition knows I was wasting my time piddling around with, it wouldn't make any difference. Because that part in there, the arrows are going, I throw it all away. It doesn't make any difference because, so I start a little bit off here, a shade. It doesn't hardly make any difference. Therefore, I can really chop this mirror down a bit. Where is the part of the mirror that makes the real difference, that makes this get a real length, that makes it likely to be big? It's the place where the arrows are all pointing nearly in the same direction for a while. Think a while. It means it's the place where the curve stops changing for a while. And after much mental effort, you'll discover that's always the place where the time is least, or possibly other way sometimes, most. Most often in practice it's least, but it can happen most. Anytime the time curve stops changing, it's a place where the time is least. And so it turns out that the ray that's most important, the thing that determines the probability, is the part of the physical world which is close to the place where the time is least. And that's why you don't have to worry about the other part of the mirror. And that's why, crudely speaking, you say, hell with the rest of the mirror, I can just use a little piece. You're wrong if the piece gets too short. If it gets too short, you don't get much of these. You get a few of them and not enough. You get different answers. But that's a few, maybe thousandths of an inch, and you're not used to experiments with thousandths of an inch mirrors, although in the laboratory we have many such experiments, and I am strongly tempted to tell you what happens with such things and so on, but that's not everybody's experience, and so I have to stop myself somewhere. And so I stop here. I say, what I've done is I've pointed out that only part that really counts to give you the answer there is what happens in the center of the mirror, that the other parts cancel themselves out in their effects. They're just as strong, there's just as big an arrow from here as there was from here, but just move a little shade over and there's another big one trying to undo it because it's twisted. And in the middle, where the time is least, the arrows for a while point in the same direction. That's why in approximation we say you can get away with a crude picture of the world by saying the light just comes to the middle part where the time is least. And it's mathematically easy to prove that in any circumstance when the time is least, it turns out it means those angles are equal. And I attempted to prove that, but I won't bother you in straining your geometric imagination. Now, it perhaps bothers you a little bit to have to say that the reflection, that all this is happening, that there's reflections from all this part of the mirror when all it does is cancel out. And so let's discuss this a little bit. Let's do an experiment to find out how much light is reflected under similar circumstances. And I guess since I have one more color, and I don't want to erase everything I've got there, let us just imagine, for definiteness, that only this, well, here, let's say this piece of the mirror. I just used a piece of mirror so big. No bigger. I just used a little piece. It's a big piece, but it's in the wrong place. And I expect to see the light reflected from here to there. Not very likely, huh? But this dopey physics says that, yes, you have to calculate all the arrows from all this stuff from here to here, and they're all changing. It corresponds to the arrows up to there from the beginning. So it's just a bunch of arrows that go zzz for a while, and I stop, okay? You know, that line means that these arrows are not in the picture anymore because that part of the mirror isn't there. And so you see that the distance from where I started to where I finished is very small. Not zero, but very small. And it's true. Experimentally, with a finite piece of mirror, you get a tiny amount of light reflected in an odd manner. It's called diffraction from the edges, but I don't want to go into that. It's very tiny, so let's say it's zero. This idea that the whole thing can be there and doing nothing seems like a kind of a waste of time and a mathematician's thing only. It's not real physics to have something that's not doing anything. But watch this. They're going to prove that it's right by the following dirty trick. I perhaps should expand this side a little bit. I'm getting pushed off the side of the board there by the way I've drawn it. This is the way the time was going, and the arrows were pointing in a sequence of directions which were very different from one another. And now I'm going to do a more fine calculation, which I cut it even finer, and you would find, if it's fine enough, that I haven't got much difference in time, but I find a bunch of arrows essentially going around in a circle, very close to a circle, getting nowhere, going around and around in a circle, because some of them are pointing forward and some of them are pointing backward virtually. It's continuous, but for some contribute this way and some contribute that way. Now let's have some fun. Let's see if it's really true. What we're going to do is we're going to make the mirror less effective by painting it black in the right place. We're going to paint the mirror black in just those places in which the arrows are pointing the wrong way. For arrows, if it turns out that the timing is such that the arrow points this way, don't use that part. Paint that part of the mirror black. Don't use it. Make it not reflect. I know I painted the wrong curve. I should have painted. My drawing is unfortunately way over here. The idea is, if the arrow is this way, I take it. But any time the arrow comes out that way, if that's the time between here and here, Then I paint that part of the mirror black so that those arrows don't operate. In other words, in order to test this idea that everything's canceling out, I take the parts of the mirror for which the timing is just right to make arrows that point this way, or more or less that way, or at least have a bias in that direction. And the parts of the mirror that were contributing arrows whose bias was in this direction, I paint out, or if you don't like this idea of painting out, and you have enough patience, you simply cut the silver away. There is nothing. The light goes through. Worse, it can't reflect. It didn't reflect before. You got less mirror. It's going to reflect less. No, it reflects perfectly well. Because according to this picture, if I add a sequence of arrows, which are turning rapidly, and then as soon as they're supposed to come on, oh, here's the circle. Here it is, down here. Excuse me, and it's also in yellow. I add the arrows this way. They're going along all right, and as soon as they start to turn back, I don't let it go. I don't add anymore. I've cut the silver away. And now it gets around and starts to go in a forward direction again. So I let them come. I don't paint that silver away until it starts to back up, and then I paint the silver away. I get it out. And what I end up, of course, is a lot of little strips of silver separated by clear glass. And each time the thing does this, bloop, bloop, yeah, bloop, 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 over this whole distance. And wow, what a net arrow I've got for the final result. Lots of light. And so it's possible to take an ordinary mirror, flat, and cut away strips correctly in the right places, just right, strip after strip. Very fine, it turns out, thousandths of an inch. So that when you shine light down on it this way, it bounces it off that way. This thing would only work with one color. If I've designed this it's called a grating. It's a line of lines, and it works like a charm. It's beautiful. If I use red light, and I've got that thing exactly right, it'll go right. If I use blue light, it won't work. What I have forgotten to tell you in the beginning, and I don't know whether I said it last time, is this is what happens with red light. With blue light, you get the same result, except the thicknesses are shorter. All the timing is quicker. And what the rule is for blue light is the same as it is for red light, except the speed at which you turn that for time is faster. You turn it more. Now you'll notice that the place that we put those cuts was especially designed just for this rate of turning. If it turned a little more, because it's blue, and I had the cuts in the same place as I made for my theoretical red one, it turns out it all gets kinked up and it doesn't work very well. But as a matter of accident, it happens to be so that if I make two changes, first I use blue light, and then I put the photomultiplier at a somewhat different angle, in fact less angle, it works again with the same lines that I used for red. It's an accident. I cut it carefully for red, put that photomultiplier over there. It also happens, luckily, that if I change the color, it doesn't work. But if I move the photomultiplier and change the color, it's cut again about the same place. It comes out. Just geometry. And therefore, what happens is actually that if you shine light down here, blue light will come over here and red light will come over there, and it's a beautiful thing to see. Because if you take this thing and turn it, when the light is fixed, you'll see colors, red and blue. I don't know whether it's come down in New Zealand or must have. We have them in the United States now on automobiles. People have these wonderful colored signs that you wonder where the colors come from. They're so bright, and as the car moves, it changes from red to green to blue, and all they are is mirrors with lots of lines on them so they're not reflecting in the normal manner. All right, so that shows really that we cannot get rid of the area which gives zero, that it really is canceling out, and if we do torturous and clever things to it, we can demonstrate the reality of the reflections from this part of the mirror and produce some striking optical phenomena. It does depend on how much of your experience is, whether this appealed to you or not, if you knew about gratings or you didn't. That's the problem with this lecture. I can go on like this explaining holograms and lasers and everything else easy, except you don't know anything about them. There's no use, but never mind. I try something else. This time I'm going to talk about light going from air to water. We would like to put the photomultiplier under water. We'll suppose the experiment, they're going to arrange that. This is water. maybe it's easier to put the source underwater. And here's the source of light that we would like to know. Photons have a small number of photons. We want to know if they're going to get there. And we have, again, the same situation, that the light can go this way to the water surface, and then that way to the photomultiplier, or it can go this way to the water surface, and that way to the photomultiplier, and it can go all different possible angles. And every one of them contributes an amplitude, and it makes a bunch of arrows at all different kinds of angles, and what's going to be the result? Same picture as we made up there. The only part that really gives a result is when the time is changing slowly. In other words, it's a minimum or a maximum. Minimum. Now, in this particular case, in water, I didn't tell you about this, but in water, when you're finding the amplitude, the rate at which the thing goes around in water is slower than in air. Or better, maybe it's a better way, excuse me, better. I made an error. What I said was wrong. Light travels slower in water than it does in air. So that the time when you calculate for a length in water is not the same as in air because the light goes slower. So that these lengths are more important, so to speak, than in here. What you need to do to find out what's the most important of these pairs. Remember, as before in the case of the mirror, many of them all canceled out and didn't make any difference, but there were some that were important when the arrows were always the same, when the time was minimum. So what we have to do is we have to figure out to go in here and to come down here where the time is minimum. The idea is, suppose that you were really in water, and you went in a boat, you could only go slowly, and then you could run quickly on land. Well, the beautiful girl is drowning here, and you're the lifeguard, and you can swim slower in water than you can run on land. Where do you hit the water? You rush this way to the water and swim like hell. No. Actually, there is a place that's a minimum, which it would be foolish of a lifeguard to analyze and calculate under the circumstances. But the fact is, there is a computable position at which the time is minimum, and it's some kind of a thing that looks like that. The idea is, it is not the straight line, because the straight line has too much water in it, so to speak, water path, and by moving for less water path and more land path, one makes a compromise and comes out so. And that is the reason why light is bent into water, and as a matter of fact, if you follow this thing all the way through, you can prove that the ratio of the sines of the angles of this and that is the ratio of the speeds in the air and the water. But the reason that it's a minimum time is the same reason as it was for a mirror. Okay? In the same way, we can understand why light goes in a straight line. It's used, if we had a source here and a photomultiplier here, there are many ways the light could go. We could say a photon can go from here to here, a certain amount of time, phase. That's the way I've been doing it before anyway. But I'm going to be more accurate this time and tell you that the story that I said it went in a straight line before in calculating things was only an approximation. If I didn't do that, I get the same answer as if I do the following. I say, not only does it go in a straight line, it could also go this way to here. It can go this way to here. Really? Really? It can really do it? Yes. It can go any way it wants. But almost always, the contributions from these different ways cancel out with each other completely because there's a nearby way that's got the arrow the other way. But if you can find a way where if you change the paths a little bit, nearby paths, don't make any difference to the time, then you've got the place where most of the contribution is coming from. And the story is as follows, that if you have a path like this, a nearby path can be made that's shorter. That is, has a different time. Distinctly shorter. A lot shorter by moving it in. And so you can get a very different time. But that the minimum time comes for the path that's a straight line. And so the most important contribution is from the straight line. Remember that in the case of the mirror, I say the most important part of the contribution is near the place that is the minimum. It isn't exactly that one arrow that does it. No, it's the contribution over quite a range. And so it turns out that a light does not really go in a straight line, but it smells the neighboring lines and it uses area around it, just like a section of mirror is necessary to get the full reflection. A section of space is necessary. If you were to put blocks in here so as to not allow the path to wander too far away, and made these very tight so that it was try to go in a straight line, you would discover that the light from this source, if you put the photomultiplier here, for instance, and didn't have these blocks, no, if you put these blocks in like this and had the photomultiplier here, let's say the blocks are pretty far apart, and put the multiplier in such a way that that line is not allowed, that corresponds to using the piece of the mirror that's in the wrong place. But if this thing squeezes tighter and tighter, after a while light begins to come here. The reason it comes is that you've only got a few of the arrows. It's just as if you used I didn't show you in this case. It's the same idea. If you did have the mirror in the wrong place but used a very short mirror, then there's not enough range for the arrows to cancel each other. Just a few that go one way and it stops. And so what happens is that there's a little, if you cut this very fine, the light spreads, that it doesn't go in a straight line. And if you try, therefore, to squeeze light into a small hole to make sure it's going in a straight line, you discover that it no longer goes in a straight line. This is a few examples of how the theory of thing is worked out. Let me just do one more, which is interesting. Instead of dealing with all the net result of adding all these, in empty space, of adding all these different possible paths, is in fact turns out to be the same as if you just took this one path. Very closely, as for approximately, well, essentially that. I mean by that, there's just another factor, but the angles are the same. If we think about this in a special case, let's draw an artificial line here that means nothing. It's just like the equator of the Earth, it's just a line. And then consider paths which are straight in two sections and ask, what about light going this way, and this way? So you don't have too many different paths to add. We restrict them to be double straight line sections. Then by exactly, the answer is exactly the same as for the case of the mirror. The time to go this way is a big time, and this changes and changes, and it changes rapidly. And if I plot it this way, the time for these different things, this is a long one, that's a short one, that's a long one. This time you can figure the time immediately in your head, because the time is just the length of that line, and you can see that that's long and that that's short. Now, let's have a different kind of a game. Let's do something to make this one longer so that it's the same as that one. Let's fool the light so that all the paths are the same length of time. How can we? I told you it went slower in glass than in air. So let's put a piece of glass in here to slow it up so as to take a little longer. Let's say we're not going to do anything to the path out here. That's going to be the key time that we're going to make everything equal to. Now, the one that would go through here straight would have got there too fast. We slow it up for a while, and by slowing it up, we bring it so that the time it takes is the same. Now, there was a path that went like this, and that had a time so. It's also too short, not as much as the other one. We have to make it take a little longer, so we have to put a piece of glass in here. This glass is not as thick as this one because we don't have so much to offset. The nearer we get to the top, the less we have to use glass to slow it up, and the very last one needs no glass at all. When you put all these funny pieces of glass in there, the net result, of course, is that you're putting in a piece of glass shaped like so. The result of that is that the time, now, with the glass in, by careful design and the exactly right shape and right thickness, you just found out how to calculate the thickness exactly, just put the right thickness in to compensate the time, you will find that the times now are all the same, no matter which path it is of these straight line types. What happens then? Now, each one of them contributes its amplitude. Yes, amplitude, same time, same, whatever the angle of one of them is. The next one's the same, the next one's the same. You straightened out the arrows. What a dirty trick. You straightened out the arrows. And there's a lot of arrows. There's millions of arrows. And so the result of this is that they get, for the final result from the front to the tail, a sensationally large, unexpectedly enormous arrow, a high probability of going. Of course, you know what I'm describing. A focusing lens. If you have a source of light here, and it just sends light to here, it's kind of weak because it spreads. But if you put a lens here, it'll concentrate it right away again back to here. And that means concentrated light means high intensity, and really high intensity means lots of photons. Or if the light was weak, the chance of a photon arriving is very strong at this particular point and very small everywhere else. And so by the trick of arranging things so the times are equal, we focus light. And so by this, I use these examples to show you how what looks at first like an absurd rule with no causality and nothing like anything real produces effects that you're more used to. It also produces other effects that you may not have been used to, such as the grading and a number of other things. And so this is the success of this point of view, and it continues to be successful. And I would summarize it by saying what we know so far is that the probability is equal to the square of an amplitude, then they need a calculus of the amplitude, then an amplitude for an event that can happen in several different ways. In different ways, I should have written this in the beginning, is the sum of an amplitude for each way. Now I have the rest of that should be really all that is really necessary to understand. But in order to get a full flavor of the theory, I would like to tell you a little bit more about how people calculate these amplitudes. And a little bit more about the law for the amplitude. For example, I kept bringing in funny things like from when you have a reflection, you have a little arrow. When it's from the other surface, you make the arrow backward. When you go through glass, you have to use a faster timing, and so forth. All right? All these things should have to be explained, and they will be, not this lecture. However, the particular feature that I can describe a little better, a few things of how we analyze the amplitude. A particular problem, to show you the type of thing, is this. Suppose you had a surface here, and that we have a reflection. Suppose this was a 4% surface, so that the amplitude, the intensity that came out here was 1/25th, or that for that surface, the amplitude of reflection is a fifth. Now that, and I put the photocell here. Well, you could put a double surface. Oh, I have it already drawn. I'll draw it again. I have a double surface, and a source, and the reflections, and all this stuff, and I computed the amplitude for the light to arrive here. Now I'm going to try another thing. Instead of putting the photo multiplier there, I make a little hole, I let the light keep going, and I let it bounce to a couple of other surfaces, 3 surfaces, whatever it is, all right? And come out over here and put the photo multiplier there. How do I figure out what happens, what the amplitude is? Now this amplitude in this particular thing can be thought of in, as so to speak, 2 problems. One, if light starts here, what's the amplitude to get here? The second, another problem that's interesting, is if I put the source here directly, what would have the amplitude to have got there been? It turns out from those 2 things, you can figure out this combined problem by an operation you could call the rule for successive amplitudes. Right? The rule goes like this. Let us suppose that this section here, if you don't understand this too well, it doesn't make any difference. You get some, I'm trying to give you some flavor. The flavor tastes bad. It is, just relax. Now here, some people like ginger snaps and some don't. Let's say this problem, we've already worked out the amplitude for all the possibilities added together to arrive here. Let's call this point A, this point B, and this point C. So we have if, well, the amplitude to get to B from A, that is a source A of unit strength, 1 photon, has an amplitude to get to B that's been worked out. Let's suppose we start out, this is the source strength, 1 unit. We begin. And what do we get out is the result B, the amplitude comes out some crazy arrow. So let's say that that thing is this arrow. That's the amplitude that gets from B to A with the source. What is this thing? It's 1/5 as long. Let's say it was 1 surface. It's 1/5 as long and a certain timing. Let's suppose this surface over here ends up as a 4%, 1/16th reflector, or 11%, and 1/9th reflector. Makes it easy for me. The length of this thing is a fifth, you see, so that the thing will be 25, 1/25th, and you have to turn it through an angle. Now this next one, if it would work all by itself, if the amplitude to get to C from B along is this. If at B there was a unit amplitude, if at B it really was 1, then there's a certain time delay and a reflection. There's some time delay corresponding to some angle, and there's a length of 1/3. This happens to do with the time delay. The time delay, I mean, from B to C. Now, what would the result be? Why do I say 1/3? Because the area of the square would be 1/9, which is what I said the reflection should be. Now, what will be the amplitude to go get to C from A, all the way? It isn't hard to guess. First of all, the total time means that the angle, whatever it is, you go around and around and around, the sum of the amount you went around for the first part plus the second part, because the total time is the sum of the two times. So that you're going to draw something whose angle is the sum of this one and this one. It would have turned around while it was going to B. It goes around, 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 around. It goes to B, and it goes around, 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 around some more, and that's how much more. So the net result is an arrow sum like this at an angle, which is the sum of that angle and this one. You turn this, and then you turn it that much more, and you come to here. Here's where we start with the 1, and here's what we're coming out with. And how long should it be? Well, the chance that it gets, of all the light that comes down here, 1/25 is reflected here. And of all the light photons that come here, only 1/9 is reflected there. So it turns out that that means that the of the light, let's say I had 1,000, I have bad numbers. I should have taken better numbers. What you have when you finish is 1/25 times 1/9 of the light. 1 over 225 parts out of 225 photons. About, on the average, 1/25 or 9 photons get through here. And of those, 1 goes here. So 1 out of 225 come out, which is, by the way, 1/15 times 1/15. 15. So therefore, this size of this is 1/15. Now, the 1/15 can be, this composition, this is the rule of composition. Add the angles and multiply the lengths. So you have two events in succession. You combine them by this rule of composition that you add the angles and multiply the lengths. Putting an arrow on the tail of another arrow to find a final arrow, we call adding the amplitudes. Composing them this way, multiplying their lengths and adding the angles, we call multiplying the amplitudes. The reason we call it multiply is interesting, therefore, that arrows can be added, can be combined by two operations, putting them on each other's tail and multiply them together like this, which we have called adding and multiplying. And the reason we call it adding and multiplying is it obeys all the right rules of arithmetic for addition and multiplication. All of the rules such as, I don't remember the rules. A times B is the same as B times A, for instance. A and B, these arrows, combining it this way and meaning by times this composition rule, then it continues to be right. Now, the rules of algebra are things that are studied by mathematicians, and mathematicians have tried to find all the objects that you could possibly find which obey those rules. The rules were originally made for counting apples. It was improved by using negative numbers. It was improved still further by inventing fractions. It's still true you can add and multiply fractions. You can use unending decimals to represent numbers and add them and multiply. We have today become very sophisticated. In the early days when mathematics was first developing, and it was said that a number is something like when you count the number of apples or people or something like that, then the whole idea of a half a person was a problem. But today there's no difficulty at all, and nobody has any moral or discomforting, gory feelings when they hear that there are 3.2 people per square mile in certain regions. It doesn't bother them. They don't try to imagine the 0.2 people. But what they do is they know what they mean, that if they multiply that by 5, it gets to be 16, and so forth. And so some things that can satisfy the rules of arithmetic can be interesting to mathematicians, even though they're not represented by numbers of apples absolutely, and without having to picture exactly what it is. And these arrows on a plane, which can be combined by two operations, tying them on each other's tail and combining them by this multiplying and adding angle business, those two rules, adding and multiplying, obey the same rules as algebra, and these amplitudes are in fact called some kind of numbers by mathematicians, and to distinguish them from ordinary numbers, they call them complex numbers. Makes it hard, in other words. So for those who have studied 4 years of university or enough algebra to have come to complex numbers, I could have said all this by simply saying amplitude, the probability is a square of a absolute square of a complex number. The amplitude is a complex number, and the probability is its square, and that when the thing can happen in more than one way, you add the complex numbers, and when it happens in succession, you multiply the complex numbers. And have I said any more than I did before? No. It's just a different language, and it may sound better, and the only reason I use that different language is because some few of you may have heard of that language, and it would be nice to make sure, I just wanted to make sure to you that it was really the same thing. For those who have never heard of it before, the idea that that is multiplication may be disturbing, and I think I waste a little time on the side, and nothing to do with, well, I think I waste time. I'm late, so I shouldn't waste time. I wanted to explain why it's reasonable. I can't resist. I want to explain why that is a reasonable way to define multiplication. This is a stupid thing. It has nothing to do with our lecture. I call it multiplication. That's enough, but I have to play anyway. What is multiplication? And the Greeks wanted to use numbers that were not necessarily integers, and they did it by talking about lines. If this is a unit, then the line, this length, represented the number 1. Whereas a number like 2 would be represented by a line, which would be twice as long. That way you can represent fractions and so forth. The third is long, 2.5 times long, so forth. So here's 1. 2 is the relationship of this line to that. Now 3, you might get, is the relationship of this line to that. All right? I have to write the unit. In order to understand what this number is, I have to tell you how big 1 is. Now what's 6? The product of 2 and 3. It's a line also. It's a line. It sticks way out. And it's like so. It's got 6 notches. Oh, it's 6 notches. And the way of looking at it is to say that the problem is this. I want to convert 3 to 6. I want to multiply by 2. The idea is that the 3 line that I had before bears the same relationship to the answer that I'm trying to get, the 6 line, as the 2 bears to the 1. 6 is twice 3 in the sense that this relative to that is the same as the 2 to 1. Right? The idea is then that the answer of multiplication should bear the same relationship to one of the things you're trying to multiply as the other thing does to the unit. Voila. Let's see. I want to multiply this by that. And what I have to do then is to create a line which bears the same relationship to this line as this one does to that. Yes? I have to, just like I did over there, I have to find a new answer. It has to have the same relationship to this line as this has to that. Now let us draw the answer that I drew over here, so you can see its relationship to that line. What's the relation of this and this? The relation of this and this is a certain proportion in size and a certain angle. Can you imagine that thing turned so it's in this, and you see that it's the same angle and the same proportion as the original 1 puts this to 1. In other words, the relation of this line to that is the same geometrically. And so that's why it's multiplicative, because it has the same geometrical property, a property, though, that fits on lines which are tilted, not just lines which are horizontal. It's interesting, the mathematicians developed all this mathematics for these crazy numbers without having anything to apply it to directly in physics, and that it should turn out to be so fundamental to the bottom laws of physics to be using such funny numbers or complex numbers. So that's the other feature. And I'll just say one more thing to finish this. That means that we can understand what happens in a given situation by a sequence of, as if it's a sequence of events. Instead of, you see, when I was talking before, I would say a thing comes from the source and goes to the photomultiplier, and I gave you the answer for one operation. You turned it and you made a little line. But I can talk about it in several operations. I could say it goes from here to here. You start with an arrow. When it goes from one point to the other, just turn it around according to the time. Reflection. Reflection is a little 1/5 arrow. Multiply by that. That means shrink it down. Next, go from here to here. That means take the result and do again the same next thing, which is rotate. Now, finally, I would like to say, what I'm going about to say is to show you that we have still simpler laws than the ones that I talked about. We have been talking only about one color light and talked about the amplitude depending on the time in that fashion. What is the difference between one color light and another color light? The speed at which that goes around. But in space, light is light is light is light and doesn't know where it came from. And what another picture is, different picture is this. Now, light, if you want to know the amplitude that it arrives at a certain time, I'm going to put time into this argument now. It arrives at a certain time in the photomultiplier. We suppose, well, I think, since I haven't figured out, I'm sorry, this is very amateurish, isn't it? I haven't figured out what I'm going to talk about completely next lecture, and I haven't got quite enough stuff to fill it up. And therefore, I'm going to leave this little thing in the next lecture so I can fill it up. I will tell you what the idea is, that the time has to do with the, well, I'll discuss that the next time. The other thing is, I have tried, and in the case of monochromatic light, I have completely described the rules for the amplitude. If I add one more thing, which I haven't, that is, I have to talk about what happens in a vacuum first. And when a particle light goes a certain distance, it's true that the angle turns, but there's another rule which I have not discussed because it's not very interesting relatively, and that is that the amplitude to go a certain distance, besides turning, shrinks. If you go far, it gets smaller. Everybody knows that the chance of finding a particle far away from the source goes down as a square of the distance. And that means that the amplitude goes down as the distance. In other words, when I was drawing these arrows, as I made them go further, I should have shortened them a little bit. Those are kind of approximations. They have nothing to do with the excitement of how it works, and I didn't want to bother you with such accurate detail. But if I once tell you that the thing turns at a certain rate and goes down in length proportional to the distance that it went, I have completely defined exactly the properties of the propagation of light of one color, except for one other technical thing. Light, as it turns out, even if you specify the color, I have to say this in order to tell you exactly, how much you know and how much I haven't mentioned. Even if you specify the color of the light, there's one other feature that light can have. There are two kinds of photons with the same color. We say they're polarized. If you use Polaroid, for example, you let through light that has only one kind of axis. And another piece of Polaroid lets through the same kind of photon. But if you set that other piece of Polaroid for its axis the other way, so that it'll pass light with the other kind, then no light will get through, where the first one only passes one kind and the second the other. All these effects of Polaroid and polarization have been entirely left out of this discussion. Why? Because my purpose is to give you a complete feeling of the difficulty of the subject, of the interesting philosophical problems about probability, the succession of amplitudes, how little we really understand, and so on. And the fact that there's two different kinds of photons is not qualitatively different. It just means a little bit more calculation, but of the same style. It doesn't change the style of the analysis. And therefore, in spite of the fact that I've left out a number of things, such as how the amplitude changes with distance, and the fact that there's polarization, makes my lecture incomplete in the sense that I therefore have not given you the exact law for the propagation of light. Not quite, but damn close. So close that it contains all the mysteries, all the peculiarities, and so forth in a perfectly satisfactory way. And I hope then that you're satisfied and you're confident that I haven't left any essential difficulty out. The things I've left out are not difficult. They take just another lecture of technical points rather than any new difficulty. One thing, though, I must say, and that is this. We've been talking about light going through a vacuum, and then I had a rule about it's reflected by a certain amount when it goes. It has a certain shrinkage when it comes off a surface. When it goes through a medium, it gets slowed up, and so on. These, it turns out, are not really the properties of light. They have to do with the properties of matter. You can't get reflection without having a piece of glass. It doesn't go slower unless it's in the glass. It really, as it turns out, is not going slower. It's curious, and we're going to find out exactly what it does. In order to explain it, we have to know what the electrons in the glass are doing and how they interact with the light. And I'll summarize the most wonderful fact is that light never does anything, really, when you get down to it, except to go in a vacuum from one place to the other. It's emitted by one atom or particle and absorbed by another. And it never goes and gets slowed down or gets reflected. What reflection really is the light goes down, is absorbed by something, which shakes it, and that emits a new light, which comes back. Reflected light is really not the same photon coming back as went in. The photon from the source went into the glass, and from the glass comes out a new photon. This is an interesting thing that makes light in the end simpler and simpler and simpler. And what I was trying to get to in the last steps was to show you how ultimately simple it is when it's only in a vacuum. And the complications of funny laws for reflection and funny laws for going through glass are really the result of the interaction of light and electrons. And that's why this subject of discussing physics can't go on any further until I want to discuss matter. And the next lecture will be about matter. All right? Thank you.
I put together a theory about photons and electrons, and I took it to my physics teacher, who said it's not right.
Since he didn't describe the theory with great detail, I cannot answer. But I will say something that I forgot to say in the lecture. One has the advantage of using questions to finish the lecture. I really had. I must emphasize something that is a very great danger of talking about what happens in an experiment with one photon. Because after a while, you get the idea that these arrows are somehow associated with a single photon. It's a mistake, and I should have not permitted that mistake to be generated by mentioning as early as possible that it's not right, and that what it is, these amplitudes are not the amplitude to find a photon riding around somewhere, but the amplitude that an event occurs. And I give an example why your professor probably said no, by giving you a problem, so to speak, of the kind that we answer with these amplitudes, which is of a different style than the ones I've been mentioning and requires more thought. And I would just at least, as I say, I don't know exactly what your theory is, and maybe it's okay to satisfy this example, but nevertheless, let me know next time. The idea is, suppose that we have a problem with two photons. Suppose that we would like to know, just to take a definite example, that we have two sources of light. Each one has been arranged to two sources A and B, and it's been arranged that both A and B emit one photon under some circumstance, and you have two counters down here, two photomultipliers, and you would like to know what is the probability they both go off. All right? So the event whose probability you're computing is the probability they both go off at the same time, that this both emit. But there's a coincidence that they both go off at the same time. Now this has an amplitude, the amplitude for the two photons, so to speak. In one, there's only one amplitude, the amplitude that both go off. And I should have emphasized that no matter what the event, no matter how many you're involved with and so on, you talk about the complete event and calculate the probability of it, not the probability for each photon. Now in this case, to compute the amplitude for a photon, both counters to go off, supposing that one photon came from each of the sources, it has to be done as follows. One way it could happen would be that this A source gave a photon that went off, and the B one gave a photon that made the other counter go off. Let's say this counter is called X, and this one's called Y. X went off because it received a photon from A, and Y went off at the same time because it simultaneously received a photon from B. The net result of the experiment is that both A and B have lost some energy, and the two counters went off at the same time. How do I compute that amplitude? Answer. You compute the amplitude that A would reach X from arrow. That's the amplitude A would reach X. You compute the amplitude that B would reach Y, another arrow. Actually very similar in this particular example because of the symmetry of the picture, but it's not relevant. What is the problem with amplitude corresponding to the thing that both should happen? You can get a hint. Well, what the answer is the product of these two amplitudes in the same sense that I talked about before. Multiplying. You're going to get an idea of why it's multiplied in this sense because of this. It helps a little bit. The time, if there's a certain chance that this reaches here, like 1/5 of them will reach here, and 1/9 of them will reach here, then the probability that they both reach is the product, and you've got to get that back into the amplitudes, and it's a clue. At any rate, you should multiply the amplitudes not only of things that happen in succession, but things that happen independently at the same time. This particular problem is especially interesting. Let's suppose when I multiplied these two, by the rules I'm talking about over there, I get add the angles and multiply the lengths. I get this answer. That's not the right answer for this problem, incidentally and curiously, because there's another way it can happen. You're all sitting there saying, well, how the hell did I know that it wasn't A that went to Y and B that went to X? Well, if I say that this was, remember, this one was A to X, and that was B to Y. Now, if I say A to Y, that's a different arrow. Why? Because it's a longer and therefore different time, and therefore this particular arrow is turned more. And likewise, B to Y is turned more. I'm not drawing them correctly because there's a symmetry. There's a similar arrow. At any rate, the net result for that case is some other arrow for the other case. Now, what do you do when you have two possibilities? If a thing can happen more than one way, you add the amplitudes for the two ways. And the net result for this problem is to tie one of these arrows onto the other, and that's the answer, the length of that. And now what we have is something which is all the elementary textbooks say is impossible, interference between two photons. Or more correctly, you get pluses and minuses depending on the angles, strengthenings and weakenings, depending on the positions of these two counters relative to each other. This is used, as a matter of fact, and was invented, I think, locally. Perhaps not in New Zealand, but at least in Australia. To detect the diameter of stellar objects or quasars and things like that by looking for radio waves received in two receivers and looking for correlations of strength, which just means a coincidence of photons. It's called the Brown twist effect. But it's a perfectly definite effect that's understandable and computable this way. Most people's theories who have a theory about waves associated with photons will not have a theory which is capable of dealing with situations where there's more than one photon. I do not know that your theory is incapable. I only suggest that as an interesting problem.
How old is this theory of quantum electrodynamics?
Present complete form is from 1948 or 78, 9, 78. Therefore, it's 30 years old. That's what the subject of these lectures is. As you see, the reason it's so difficult to filter down is the resistance of the mind to such models. People who hear that all I'm going to do is make a couple of arrows on a board to calculate the chance that something happens, says this guy doesn't know physics. But this is the guy who knows that that's what you have to do and admits, therefore, that he doesn't know why he's doing what he does. And you can have the confidence that when I say I don't know what I'm doing, that probably nobody else does either.
In what way is your theory different from wave mechanics?
The question is how is this related to wave mechanics? Now, the reason I hesitate is there was a thing called wave mechanics, which is the quantum theory of wave theory. And there's also another sense in which we might be using the word the mechanics of waves, by that meaning water waves or sound waves or something like that. There's a special theory called wave mechanics, which is discovered and developed in 1926, which is just another name for quantum mechanics. And that there was two things. First, there was an equation for these waves, these matter waves, made by Schrödinger. And then there was an interpretation of these equations by Max Born within the year, which was that the function that we're talking about is a complex number whose square is a probability. I am saying no more than that at all. That's exactly it. The only thing I can add that for the 20 years after is merely a refinement or an improvement in discovering exactly how to calculate the wave amplitudes, or these numbers, these arrow amplitudes, for photon phenomena and electrical phenomena of high energy and so on. The complete formulas for quantum electrodynamics took 20 years to get straightened out exactly, and that was why I said 1949. But 99%, well, 97% of the thing was worked out in 1929, and the interpretational scheme about probability amplitudes, and that you square them to get probabilities, which is so strange, is the resolution, shall we say, or a description, a precise description of what was, for a while, a confused wave-particle duality. You might say, but you still have a sort of a wave in the sense of something turning or oscillating, and the particle somehow in the sense of the particle going. So it's still a duality, but the words wave-particle duality is a description of a condition of the minds of physicists before 1926, in which it was best described as saying, it looks exactly like a wave, but that's on Thursday. And it looks exactly like a particle, but that's on Tuesdays. But the answer is it does not look exactly like an ordinary particle bullet with normal probabilities, and it does not look exactly like ordinary waves, because it ends up that you measure it in particles. And how to put that together? Answer is the way it looks.
Then in your own mind, do you think you have resolved this peculiar duality?
Not at all. I haven't done anything about it. The wave-particle duality represented a state of confusion. It was a word for that there was a wave-particle duality. It was a phrase used to describe a state of confusion as to exactly what law to use to figure out what happened in each circumstance. Also a confusion of model, whether it's wave or particle. This thing, the final way out, worked out by Born, 1926, it's still got dual aspects of wave and particle, but it's precise in telling what to do and to predict the circumstances in any experiment. And there's an agreement with with experiment. And so it's a resolution of the confusion, but it's not a resolution in the sense of producing a model which is clear, physical, in the old-fashioned sense of waves or particles.
Are the clicks from a photomultiplier caused by the photomultiplier and in no way related to light?
The question is, when a photomultiplier makes clicks, is it the photomultiplier itself that's making the clicks, or is it light? And the answer is, it's light, in the sense. And insofar as it's actually quite true that photomultipliers make clicks all by themselves in circumstances in which we've done everything we can to make it as dark as possible. In other words, it's dark, and there is no light. Various things this because it's so extremely sensitive, and one can do things to the photomultiplier to improve it, such as cooling the cesium surfaces so they don't emit spontaneous electrons and so on, until we get an instrument, the idealized photomultiplier, which is better and better in the sense that it has less and less counting in the dark. But whether it has counting in the dark or not, when you change the circumstances, that in normal parlance, in ordinary language, we'd say light is coming in the sense that the sun was shining, but we put a whole lot of black paper around it, and we got a lowest count, make a hole in the paper, and all of a sudden the counts go up. In all those circumstances in which we would expect in ordinary language to say light is going in, and in all those circumstances the counts on the photomultiplier are increased. And the increase is by an amount that depends upon how much light is let in. The increase. If you improve the photomultiplier so the dark current is much less, you get the same number of excess counts due to making holes in the black paper. Because the circumstances in which the photomultiplier increases its count are those which are commonly associated with circumstances in which the common English use of the word light is used. We use the same word and say, when you have a situation that you would say light's going in, I'll guarantee you the photomultiplier will go off.
Is light then wave-like?
No, it's discrete. It always works discretely. Ah, yes, discrete. Because no other instrument has ever been designed or can be designed, if people have tried and they've argued about it and discussed it, whether I build a photomultiplier or any other instrument for the detection of light of low intensity, it always ultimately behaves in this pulse-like manner. I only use one example, but every instrument that detects light at sufficiently low intensity always ends up discovering that light comes in these lumps. Also, the behavior of light in many other circumstances, like in in hot regions and so on, Planck discovered that he could not understand that many of the properties of the distribution of light from furnaces and so forth and other technical situations unless the energy of the light could not come in arbitrary amounts, small amounts like the wave theory expected, but had to come in definite lumps of a certain amount of energy depending on the color. And so it's all this, not just a photomultiplier, but all the other experimental situations and so forth, which it's impossible in a popular lecture without 4 years of study to produce and to demonstrate again and again all these experiments to produce the kind of conviction which one would get from a long experience. It's unfair of me to say you've got to believe me because there are all these experiments, but the best I can do then is to refer you to other books and stuff where experiments are reported of all kinds, which will show you that that's the way it looks. That's the best I can do.
Can your theory explain the redshift or blue shift of light from stars?
Yes. Yes, and that was a point that I was coming to, but I'll try to, because of the time, I guarantee you, if you promise to come next time, which is next Tuesday, I will contain it. I had intended to put it in this lecture, but I saw that was one of the things I was coming to. The idea is relatively simple, and I'll try to explain it. The color of light has to do with the speed at which that amplitude turns around. I never talked about how the detector would look, where the photomultiplier would see if it was moving toward the source. But what happens is that the time that we're talking about to get the amplitude is always shorter as it approaches the source. And because of this changing timing from the motion on top of the rotating, it appears as if the arrow effectively at this multiplier is turning at a different rate. And that is equivalent to what would have happened to the multiplier if it's standing still, but the light source had a different color. And therefore, the behavior of an instrument which is moving toward a source is to react as though the source was standing still, or the object was standing still, but the color were bluer. All right? It's not very clear, but I perhaps make it better next time.
Right, we must make a break there. I'm sure Professor Feynman needs all the time he can to get his next lecture.